We're going to investigate further logarithms. And as you can see here, this is titled Properties and Laws of Logarithms. I think our books can use both words, properties, and they can use laws. Some use both. And I prefer to think of 4 properties and 3 laws, although your book may refer to all of them as properties. But here are the 4 properties that we need to be familiar with. The first things that we need to be familiar with. And the very first one is the log of 1, regardless of the base, is equal to 0. And that only makes sense because a to the 0 power would be 1, wouldn't it? Now, I want to point out to you the 2 special bases, what this would look like. If we were talking about base 10, then this would look like the log, and we wouldn't put the base 10, we would just leave log, the log of 1 is equal to 0. And if we were talking about base e, remember we use a special notation for base e, that's ln, natural logarithm of 1 is equal to 0. But the logarithm of 1, regardless of the base, will always be equal to 0. Second property. The logarithm of a base a is equal to 1. And that's because if we take a and put the power 1 on it, we'll get the result a. So the logarithm of a base a is equal to 1. If the argument and the base are the same, then we'll always get a result of 1. And so if we were talking about base 10, this would look like log of 10 is equal to 1. If we were talking about base e, this would look like natural log of e is equal to 1. Because here, in the first case, we understand that the base is 10. In the second case with ln, we understand the base is e. Third property. The logarithm of a to the power r, base a, is equal to r. Again, this only makes sense, because if we take the base a and put the power r on it, we get the argument, which is a to the r. And on base 10, this would look like the logarithm of 10 to some power r is equal to r. Or if we were talking about base e, this would look like natural log of e to the r power is nothing more than the exponent r. And the fourth of these properties is not quite as obvious. Okay? In the fourth property, it says, oops, my bad, if we have some number a and we raise it to a power that is the log of m base a, then the result we will get is n. Now, like I say, that's a little more difficult to see. Let's just talk about, if you will, a proof of this. And here's the way I would go with the proof. Is let's consider a to the power log of m base a. But before we consider that, let's look at the idea of the log of m base a being some number that we don't know what it is for sure. But we can take that information and we can rewrite it in exponential form, so that would be the base a to the power n is equal to m. Well, if you take that information over here, then if we look, we have an a to a power. And on the right side over here, we call that power the number n. So this is nothing more than a to the n. And on this right side, we said that a to the n has to be equal to m. And so we've shown exactly what we were referring to here, is that the a to the power log of m base a is just the number n. Now, what would this look like if we were talking about base 10? This would look like 10 to the power log of m is equal to m. And if we're talking about base e, this would look like e to the power natural log of m is equal to m. And in all of these cases, remember the base a, the more general case, the base a must satisfy the fact that the A is a positive number, and furthermore, A is not equal to 1. So those are the four properties. Now, those properties, well, let's move on, if you will, or if we can, to what I call the laws of logarithms. And we'll do that on the next page. As I mentioned earlier, some books just call everything properties. Some books say we have the properties and we have the laws. And I learned this from the four properties and the laws. And so whether your book calls them all laws or not, you're just going to have to get used to the distinction between the two types. So the laws of logarithms, and let me point out that there's only three. Three only? I guess I should have said only three. There are three laws of logarithms, or at least what I refer to laws. And the first one is called the product law. Well, the name of it's not all that important, but it refers to what happens to when we take the logarithm of a product. So a product means, of course, we're multiplying things together. And this doesn't really matter what the base is, the law is still the same. Now, the m and n can be numbers, they could be variables, or they could even each be variable expressions. They're just representing two entities that are being multiplied together, and we're taking the logarithm of that product. Well, the log of a product is the sum of the logarithms. That is, if we have a log of a product, we can break it into the sum of the log of each of the factors. That's why it's called the product law. We're taking the logarithm of a product. The second law is called the quotient law. Of course, quotient means division, doesn't it? Oops, quotient law. And it refers to taking the logarithm of a quotient, which means we're dealing with a fraction. Okay? The logarithm of a quotient. Once again, the m itself can be a number, a variable, or a variable expression, or a very complicated variable expression. It just means we have the logarithm of a fraction, and m represents whatever the numerator is, and n represents whatever the denominator is. Well, the logarithm of a quotient is the difference of logarithms. That is, the logarithm of a quotient can be broken down into the logarithm of the numerator minus the logarithm of the denominator. And the third law is called the power law. And it refers to what would happen, or how we can rewrite the logarithm of an expression to a power base A. Okay. Well, now, and it's important that the entire argument is one expression to one power. One expression to one power, not a product of expressions each to different powers. Well, this law says that can be rewritten so that we write the power itself as a factor in front of the logarithm. And the new argument is the m, the expression, without a power on it at all, or at least not the power p. So the logarithm of m to the p power is p times the logarithm of m. Now, there's a couple of things that need to be said again. Okay, remember that the base A has to be greater than 0 and can't be equal to 1. Furthermore, m and n must be numbers, variables, or variable expressions, they can be very complicated, but what I'm getting to are variable expressions that have a positive value. So they have to make sense. The log of m has to make sense. The log of n has to make sense. Otherwise, these laws fall apart. Now, I would also say this. It's maybe not a good practice to tell you what not to do, but note that there is no law, that is, nothing is said about the following situations. Nothing said about the logarithm of an m plus n. Nothing said about that. Or as far as that goes, the logarithm of an m minus n. If you look above, there's nothing that tells us how to deal with those. And so generally, we don't have a way to simplify those. You can't say that the log of m plus n is the log of m plus the log of n. Look above. The log of n plus the log of n is the log of m times n. So we have no laws that apply to these. Okay? Here's another one. We see nothing above about the logarithm of m base a divided by the logarithm of n base a. We see nothing up there. Okay, nothing up there talks about a logarithm divided by a logarithm. And we have the logarithm of a fraction, but that's not the same as a logarithm divided by a logarithm. So none of the three laws address this issue either. And the third thing that I want to mention to you is that we don't see anything that says take the logarithm of m base a and raise that logarithm to a power p. See, we don't see that up there. If we see what we see up here is what we're taking the logarithm of is m to the p power. We're not calculating the logarithm of m and then raising that to the p power. So none of the laws above address these. Okay, and that's really the important part. None of the laws address these situations. Oops, I spelled that wrong. I'm sorry. Which means we can't simplify these further. We can't apply any laws to these. We can't simplify these or apply laws to these because they're not addressed. And in class, you'll hear me say there are only three laws of logarithms. I'll repeat that about 10 times in different ways. And what I'm referring to is that sometimes students try to take these last three and make a law up, make what we would like these to be equal to. But we don't have that. We have only three laws. Well, we want to do several things with these laws of logarithms. So let's go through some examples, these laws and these properties. Okay, so let's go through several examples where we might be able to apply laws or properties to do some calculations. Well, here you can see generally the directions are use the properties and or laws, okay, of logarithms to find the exact value of the following, which whenever we see exact value, that's kind of key word for don't use a calculator, okay? Use the information we have. Okay, so let's look at the very first example. What's the natural log of e to the power 11? Well, if we go look in the properties, say, remember, this is the same thing as the logarithm of e to the 11th base e. And remember when the argument to a power and the base are the same, then we simply get the exponent itself. And that only makes sense because e to the 11th is equal to e to the 11th. So hopefully we could have answered that more readily, more quickly, in which property was that? I think that was property number 3, wasn't it? I believe so. Property 3, if you go back and look. Okay, our second example here is find the exact value of 3 times the natural log of e to the power 1.5. Now we actually do 2 different things, okay? In the first case, we could use exactly what we just used. And we could say, well, the natural log of e to the 1.5 power is simply 1.5. So we could say that. And that's because the natural log of e to the power 1.5 is nothing more than 1.5. And so we have 3 times 1.5, which is 4.5. That is one technique. A second technique, I think I'll just leave it there. Excuse me for starting someplace and quitting, but I think we'll just leave that there. Let's look at another example. And here we have the logarithm of 2 base 16 plus the logarithm of 8 base 16. And we're supposed to find the exact value of that. Now, what I would tell you is I don't know what power to put on 16 to get a 2 or what power to put on 16 to get an 8. I don't know, and neither do you. You may think so at the beginning, but you don't. Think it through. Stop and think it through. 16 to what power is 8? Well, not 16 to the 1/2 power, because that means the square root of 16, and that's 4, isn't it? So we really don't know what power to put on 16 to get 8. But we do have law number 1. Remember what law number 1 says. Law number 1 says that the logarithm of a product, base A, is the sum of the logarithms. That's the logarithm of the first factor, base A, plus the logarithm of the second factor, base A. But what I would refer you to is, let's turn that around. That is, the logarithm of m base A plus the logarithm of n base A can be converted into a single logarithm where we multiply the 2 arguments together. So the way that would apply here, we could write this as one single logarithm. And it would be the logarithm of the argument 2 times the argument 8, base 16. And of course, 2 times 8 is 16. And the logarithm of 16 base 16 is simply 1. We should know that. Well, let's take a different twist on this. Suppose we have the log of similar nature, the logarithm of 9 base 6, subtract the logarithm of 3/2 base 6. Well, this was law number 1 up here, and law number 2 on the right side has a subtraction of logarithms. So let's look at law number 2, except read it from right to left. And that is the logarithm of m base A, subtract the logarithm of n base A, is the same as the logarithm of the fraction n over n. That's an n base A. And so we have a difference of logarithms here. So we could bring this together and say this is one logarithm. It's the logarithm of a fraction. And the numerator of the fraction is 9, that first argument. And the denominator of the fraction is 3/2, that second argument. Well, then we could simplify 9 divided by 3/2. Isn't that the same as 9 times 2/3? Which would be what, 18/3, which would be 6. So this becomes the logarithm, when we simplify that fraction, of 6 base 6, and similar to what we had above, the logarithm of 6 base 6 is just a 1. So we had no chance of deciding the log of 9 base 6 or the log of 3 halves base 6, but we can certainly find the logarithm of the difference of those two. Now, let's extend this a little further. Look at a couple more examples. Well, you can see this last one is a little more involved in what we're being asked to do. We're given the logarithm, natural logarithm of 7 is equal to a. So we don't know the exact value, but it's represented by a. And the natural log of 11 is b. Again, we don't know the exact value, but it's represented by b. Then we're supposed to write the natural log of 77 in terms of a and b. So it might be a little formula in terms of a and b. And so what we could do, we have to be a little clever here. What we need to do is to write, involve somehow a natural log of 7 and a natural log of 11. And the way we can involve that is recognize that 77 could be written as 7 times 11. And so we have the logarithm of a product. Now, in this case, the logarithm of this product could be written as the sum of logarithms. So we can write that as the natural log of 7 plus the natural log of 11. And from above, then natural log of 7 is a and natural log of 11 is b. So the natural log of 77 is a plus b. Okay, let's do the same thing now for, what do I want to do? How about the natural log of the square root of 11? So that we have to somehow involve a natural log of 11. And natural log of square root of 11, remember, we could write square root as an exponent. Okay, that's the exponent 1/2. And then we could use the idea from law number 3 that that exponent of 1/2 can be written as a factor in front of the logarithm. And now we have a logarithm of 11, which is simply represented by b. So the natural log of the square root of 11 is the same as 1/2 times b. Well, these help us practice the idea behind manipulating the properties and laws of logarithms. Let's move on to a different type of manipulation, and we'll do that on the next page. Well, in this case, the directions here are not particularly clear, but these are the directions that you may find yourself dealing with. It says write each as a sum or difference of logarithms, and then I added the be sure to simplify if possible. Now, to write each as a sum or difference of logarithms really isn't really explicit enough. What we're really trying to do is use the laws and the properties of logarithms to change one single logarithm into sums or differences of logarithms that are as simple as possible. So we're trading in one logarithm that may be the logarithm of a complicated argument to many logarithms, but each argument is simple. So here would be an example, okay? Let's look at the very simplest type of example. The logarithm of 4x base 2. Now, because 4x is a product, law number 1 would apply. That is, the logarithm of a product is the sum of logarithms. So we can write this as the logarithm of the first factor, 4 base 2, plus the logarithm of the second factor, x base 2. Now, we've written it as a sum of logarithms, but we always have to be on the lookout. Here's a case where we can simplify further, because the logarithm of 4 base 2 is nothing more than 2, because 2 is the exponent we put on the base 2 to get the argument of 4. So we can take one more step of simplification here, and now we have it as simplified as we would be asked to write it. Okay, let's look at a next example. the logarithm of, let's say this is just base, let's say base 5, okay, of the fraction x squared y cubed divided by z to the 4th. So we're supposed to write that as one logarithm. As the sum or difference of logarithms. Now our argument is this entire fraction. And law number 2 says that if we have the logarithm of fraction, we can make that the difference of logarithms. That's the logarithm of the numerator, subtract the logarithm of the denominator. So we would write this as the logarithm of the numerator, which is x squared y cubed, base 5, minus the logarithm of the denominator, which of course is just z to the 4th, base 5. Now, in each of these cases, we have an exponent involved, but in the first logarithm, we actually have two different exponents, and we certainly don't have an exponent of a single entity. And so, but what we do have is the product of x squared and y cubed. So this very first logarithm can be written as, using law number 1, the logarithm of x squared, base 5, plus the logarithm of the other factor, which is y cubed, base 5. And then, of course, we have minus the logarithm of z to the 4th, base 5. Now, in each of these cases, we have one single exponent on one single entity. And law 3 of logarithms says that we can bring that exponent as a factor down in front. So now we have this very first case, the logarithm of just x, 2 times the logarithm of x base 5. And in the second logarithm, that exponent 3 we can write as a factor in front, but then we're just taking the logarithm of y. Maybe it's best that I write these this way, base 5. And then minus, well, the exponent 4 can be written as a factor in front, 4 times the logarithm of just z base 5. And so we've written this as the sum and difference of logarithms along with bringing those exponents down, but each of the arguments is as simple as possible. Now, I'd like to make a note about what we've done here, okay? Because I want to compare the logarithm, the difference between the logarithm of 2x with a power 3 on it. So the power 3 applies to the 2x, and in this case, we could bring that 3 down and say we just have the logarithm of 2x base a. But then that logarithm of 2x could be written as the logarithm of 2 base a plus the logarithm of x base a. And then we would distribute that 3, and it would look like this. Now, there's other ways we could think of 2x to the power 3. That could also have been thought of. Apply that exponent to the 2, so that's the logarithm of 2 cubed times x cubed, base a. And then we would have the logarithm of 2 cubed base a plus the logarithm of x cubed base a. And then each of those exponents could be brought down, and we would be right back there. But here's my warning. Okay, I'm doing all this to get to what I don't, to show you what I don't want you to do. If we have the logarithm of 2 times x cubed, now the placement of that exponent is critical here, because that exponent 3 only applies to the x. And what we saw above, the exponent of 3 applied to 2x, so this was like the m. See, this is the log of m base, to the power 3. But here, we don't have a single piece with a single power on it. We have a factor of 2 and a factor of x cubed. And so we would have to use we couldn't use law number 3 here yet. We'd have to use law number 1 and say, oh, 2 times x cubed is that, 2 times x cubed is a product. So we'd have to say this is the logarithm of 2 base a plus the logarithm of the other factor, which is x cubed base a. And so when we apply law 3 now, it only applies to the second logarithm. The 3 can be brought down here. and you see a difference in the results. We don't have a 3 as a factor in front of log of 2. So be careful how you apply these laws. I have some more examples you can imagine. Let's continue with a couple more here, or 2 or 3 more. We'll do that on the next page. Okay, same directions. We're to write each of these expressions, single logarithms. We're breaking down into several logarithms. So what we're getting at here, this is the entire argument. That's what we're taking the logarithm of. And as we've seen before, we think of that not as an x to the 5th. We're thinking of that as a fraction. Okay, so we first think of it as a fraction, and then we'll deal with each of the parts of the fraction. So law number 2 says if we have the logarithm of a quotient, then that's the logarithm of the numerator, subtract the logarithm of the denominator. And in the first case, the logarithm of that numerator, that x, that argument, x to the 5th, is one single entity to a power. And so in this case, we can use law number 3 and bring that exponent down as a factor in front. But there's nothing more we can do with the second logarithm. Remember, we don't have a way to deal with the logarithm of things added or subtracted from each other. Remember, that was one of the warnings I made early on. We don't have a way to deal with that. So this is as simple as we can write that. Remember, the logarithm of x minus 7, we can't say that that's the logarithm of x minus the logarithm of 7. Of course, in this case, each of those is a base 2. We don't have a law that says that, so don't try to use that idea. Okay. Let's look at this next one. Same directions. Now we have, let me make this a natural logarithm. Natural logarithm of x times the square root of 1 plus x squared. Now that square root kind of bothers us when we first look at it, I'm sure. That doesn't surprise me. That might be a little bothersome to us. But we kind of have to look at the forest and not the trees. And what I'm noticing here is we're taking the logarithm of two things being multiplied together, an x and a square root. So law number 1 would allow us to write this as the natural log of the first factor, x, plus the natural log of the second factor, which is the square root of 1 plus x squared. And then if we weren't careful, we might think we're done. But we have to be clever here, because the square root can be thought of as a power. So really here we have the natural log of 1 plus x squared to the square root of that is to the power 1/2. And then we could apply law number 3 to that second logarithm. We could bring that 1/2 as a exponent down in front of the logarithm. But we can't go further in the similar fashion that we can't deal with the logarithm of sum or a difference. We kind of inclined to bring that exponent 2 that's on the x down in front. But remember, that exponent 2 is only on part of the argument. It's not on the whole argument. And law 3 requires it to be on the entire argument, if you will. So, and we can't break down logarithm of a sum anymore. So this is the final result. And this is the only simplification we can do. Let's do one more of this type. And you can see I'm kind of increasing the level of difficulty each time. Here, let's say we've got the natural logarithm, something very complicated. It's a fraction whose numerator is x minus 4 to the second power, and its denominator is x squared minus 1. And exponent on that entire fraction is 2/3. So we've got a pretty big mess here. We kind of have to think from the outside and work in, which is a little different than normal. We have an expression to a power that we're taking the logarithm of. And so that power 2/3 belongs to that whole argument. So the very first thing we could do is write that 2/3 as a factor in front of the logarithm. So if you will, we brought that exponent down. Now we have only the logarithm of a fraction. And the logarithm of a fraction, now we have to be careful here, because this 2/3 is going to multiply whatever result we get when we take the logarithm of a fraction. So let's put the result inside these brackets. Now the logarithm of a fraction says take the logarithm of the numerator and subtract the logarithm of the denominator. Now, on the inside, let's see here. The logarithm of x minus 4 raised to the power 2, we could bring the factor, the exponent 2 down in front and have 2 times just the natural logarithm of x minus 4. Now, here again, we have to be somewhat clever. And the cleverness here is to recognize, and this is the tough part, recognize that x squared minus 1 actually is factorable. So we could write x squared minus 1, if you will, as x plus 1 times x minus 1. Now we have the natural logarithm of a product. Oh, this just keeps going, doesn't it? So let's rewrite to that level. Now, we have to be careful here again. We've got the natural log of a product, which is being subtracted. And that product, natural log of a product, we're going to break into a couple of logarithms. So let's put the result of what we get inside these inside brackets. The natural log of x plus 1 times x minus 1 is the natural log of the first factor plus the natural log of the second factor. Now you see that minus sign is going to distribute through there. So we'll have the 2/3 is way out here on the outside, a 2 times natural log of x minus 4, and this minus sign going to be distributed will give us a minus natural log of x plus 1, and then a minus natural log of x minus 1. And now we could actually multiply that 2/3 through. And so when we say 2/3 times 2 that's here, we get 4/3 times natural log of x minus 4. And then minus 2/3 times this next logarithm, which is a logarithm of x plus 1. And then minus 2/3 times the last logarithm, which is a logarithm of x minus 1. So we've taken something that was pretty complicated, and it took several steps, of course, but now we have each argument. We have multiple logarithms, but each argument is simple as possible, is as simple as we can possibly make it. Well, as we continue this, we're actually going to go in the other direction. That is, we're going to take several logarithms and bring them together as one single logarithm. But we'll do that on the following pages. In this next set of problems, we're going the opposite direction. In the last set of problems, we took one logarithm and used the laws of logarithms to break it down into 2 or more, multiple logarithms. Now what we're going to do is have a sum or difference of logarithms, multiple logarithms, and bring them together to make one single logarithm. So let me remind you then what we're going to actually do before we look at some specifics. We're going to look at the laws of logarithms backwards. what we're going to do is imagine that we have the log of some expression, base A, plus the logarithm of another expression, base A, and we're going to use law 1 to say, oh, that's the same as the logarithm of the first expression times the second expression, base A. So we've taken two logarithms and written them as a single logarithm. Likewise, we could have the logarithm of some expression base A subtract a logarithm of some expression base A. And our second law of logarithms tells us that that's the same thing as the logarithm of the first argument divided by the second argument, base A. So we've taken a couple of logarithms that are subtracted in this case and created one single logarithm. The third law of logarithms isn't creating a single logarithm. We already have a single logarithm, but it would be the idea that we have some factor times a logarithm of some expression, base A, and we can move that factor that's in front of the logarithm to a position of an exponent on the expression, on the original argument. So we do like to have a logarithm when we're done that has no factors in front of it. So we're going to use the laws in a backwards way, if you will, to write each of the following as a single logarithm. So, for example, 1/2 times the logarithm of x base 3 minus 3. This isn't really what I wanted to do. Let me start over. I apologize. How about the logarithm of the square root of x base 3 minus 3 times the logarithm of x base 3? Now, if you'll notice in law number 2 above, when we have a subtraction of logarithms, notice there's no factors in front of the logarithms. And so this 3 that we've got right here becomes a little bit of a problem. But what we could do is we could use law 3 to deal with that 3 times logarithm and put that 3 as an exponent on the x. So that's the first step we'll do. So we have a logarithm of the square root of x, of course it's base 3, minus the logarithm of that 3 factor we're going to put on an exponent as an exponent on the argument x, and of course it's base 3. Now I apologize because the way I started this, I run myself out of room over on the right, so I'm going to come back over here. Now, I can use law 2 from above and write that as the logarithm of a fraction. So we have the logarithm, of course, base 3 of the fraction where the numerator is the first argument, that's the square root of x, and the denominator is the second argument, x cubed. Now here's the issue. Remember up above I said, and simplify? If we'll notice that we really have x to a power over x to a power, because the square root of x could be written as x to the 1/2 power. So we really have the logarithm of the fraction x to the 1/2 power over x to the 3rd power. Now, x to the 1/2 power over x to the 3rd power can be simplified by saying, oh, that's x to the power 1/2 subtract 3. But 1/2 subtract 3, if we work that out, of course, it would be negative 5/2. And you can figure that out. Now, we don't like to leave negative exponents, so we would write that as 1 over x to the power 5/2. So what we really have here in a simplified form is the logarithm of 1 over x to the power 5/2, and of course it's base 3. And so we probably would consider that the simplest form of a single logarithm. We brought those two together and we now have one single logarithm. Now the way, well, let's look at a second one here. In this case, we have 5 times the logarithm of x, let's say base 2, plus 1/2 times the logarithm of x plus 4 base 2. So we want to write this as one single logarithm. And so we're first tempted to look at law number 1 because that's the addition of 2 logarithms. But just like I mentioned a moment ago, in law number 1, we don't have a 5 in front of the first logarithm or a 1/2 times the second logarithm. The coefficients of the logarithms are 1. So whenever we have a factor times a logarithm and we're trying to create one single logarithm, we need to first apply law number 3 to get rid of that factor that's in front of the logarithm. So in the very first case, the very first expression, we can take that 5 factor and write it as an exponent on x. So this is log of x to the 5th power base 2 plus, and in the second case, that 1/2 factor, we can write as an exponent on the argument, which is x to the 4, x plus 4, pardon me. Of course, that's the base 2. Now we can apply law number 1. We have the sum of 2 logarithms, and that's the same thing as the logarithm of the product of the 2 arguments. So we would have the logarithm of the first argument, which is x to the 5th, times the second argument, which is x plus 4 to the power 1/2. And of course, that's base 2. Now, we might have done the next step all at once, but it's most likely that we would want to rewrite that power of 1/2 and write that as a square root. So we would write this then as the logarithm, of course, base 2, of x to the 5th times the square root of x plus 4. And now we've created one single logarithm. So we're going backwards from what we did a while ago. We're actually taking simple logarithms, several of them, and creating a one single logarithm where the argument is more complicated. Well, let's continue this discussion then on the next page and see where that takes us. Okay, here we're trying to create one single logarithm out of this expression. And of course, we've got 3 logarithms involved, and each one of them have a coefficient in front of them. And so certainly the first thing we could do here, okay, is that we could use law number 3. And of course, here it's just log, so that makes us know that we're really dealing with base 10. We can take that factor of 3 and write it as an exponent on our argument. And we can take that factor of 4 above and write it as an exponent on our argument. And in this case, we can take that factor 2 and write it as an exponent on our argument. Now, I want to point out to you that there's 2 ways to proceed here. So let me kind of indent and show you one way. If you look at our laws of logarithms, they only have one addition or one subtraction. And here, because we have 3 logarithms, we've got multiple operations. So one thing we could do is first deal with this operation. That's one approach. And to deal with this operation, we would use law 2, and it would apply to the first 2 logarithms. And so we could say, well, when we're subtracting logarithms, we can actually think of that as a logarithm of a fraction, where the numerator of the fraction is the argument of the first logarithm, and the denominator of the fraction is the logarithm of the second, is the argument of the second logarithm. So that's just dealing with that first minus sign. Now we have minus the logarithm of x squared minus 5, that quantity squared. So now we're back to 2 logarithms, okay? And so our next step could be, okay, this is, we'll have an equal. Our next step could be use law 2 again. Well, if we use law 2 again, we would have the logarithm of a fraction where the numerator of the fraction is a fraction itself, because that's this first argument, isn't it? Whoops, that's power 4. And the denominator of the fraction is the argument we have here, which would be x squared minus 5, the quantity squared. Now the problem is that's not simplified. So let me just remind you here that that argument's not simplified. Let me remind you, if we take A divided by B and divide that by C, that's the same thing as what we're dividing into times the reciprocal of our divisor. So if we look at it in that form, then we would say that what we have is the logarithm of our numerator, which is x minus 1 cubed, divided by x plus 2 to the 4th power, times the reciprocal of our divisor, and our divisor is x squared minus 5 squared. Now, we would go one step further and actually do the multiplication of those two fractions, and so our numerator would be x minus 1 cubed, and our denominator would be x plus 2 to the 4th power times x squared minus 5 to the 2nd power. And so we've got one single logarithm. Now that is an approach, and it required us doing this algebra from here to here, okay? A second approach, and one that I kind of prefer, is I like to have only one subtraction in my expression. So let me go back to where we were. We had equal logarithm of x minus 1 cubed, so I'm looking at this step, minus logarithm of x plus 2 to the 4th power, minus logarithm of x squared minus 5 to the 2nd power. Now what I mean is I like to have only one subtraction sign. Here's what I could do. I could take the last two expressions, logarithms, and I can factor a negative out. And if I factor a negative out, then I would have the negative of the logarithm of x plus 2 to the 4th power plus the logarithm of x squared minus 5 to the 2nd power. That's factoring a negative out. So now I have only one negative. So I could deal with this part using law 1. Okay, and so here's that minus sign that I've got there. But when I deal with the sum of those two logarithms, that's the logarithm of a product. And so it's the first argument times the second argument. So now I have a logarithm subtract a logarithm, and that allows me to use law number 2. And law number 2 would say when I have the difference of logarithms, that's the same thing as a logarithm of a fraction, where the numerator of the fraction is the argument of the first logarithm, and the denominator of the fraction is the argument of the second logarithm. And so you can see that, and of course I can say that here's what we're taking the logarithm of. You can see we get exactly the same result, but we didn't have to do quite as fancy algebra to get it done. Now, before we stop here, I want you to pay attention to this and see that this idea might follow later on. And here's what I want you to notice. Look at this stage and look at our answer. Notice any logarithm that has a positive, or in this case no sign, which would be positive, any logarithm that has that is positive in front, that argument ended up in the numerator of the argument of a result. Any logarithm that had a minus in front of it, the argument of that logarithm ended up as a factor in the denominator. If you'll notice that. See, this is in the numerator, this factors in the denominator, this factors in the denominator of the one single logarithm that we're left with. And so after a little bit of practice, you can anticipate what the logarithm will look like without having to do a whole lot of steps. But I would suggest practicing the steps until you feel proficient at that. Okay, a couple more on the next page. Okay, I've kind of made a mess of this as I wrote it out, but you can see here, we're to take the expression 8 times natural logarithm of the square root of 3x minus 2 minus the natural log of 4 over x plus the natural log of 4, and write that as one single logarithm. Now, notice, of course, we have 3 different logarithms and one subtraction sign, and probably if I were doing this on my own, what I would really be looking at is rearranging it. I'm going to rearrange it and put that minus at the very end. So first I'm going to deal with the coefficient of 8 that's in front of the very first logarithm and write that as the natural logarithm of our old argument, which is the square root of 3x minus 2 with a power of 8 on it. And then I'm going to put natural log of 4, I'm switching these two places, minus natural log of 4 over x. Now, now let's deal with the fact that we have a sum of logarithms right here. And so we can rewrite this so that this was the natural logarithm of the first argument times the second argument. But I'd really like to write that 4, that second argument, in front. And that's all right because multiplication is commutative. So it's going to be 4 times the first argument, 3x minus 2 to the power 8. Then minus natural log of the 4 over x, which we haven't dealt with yet. Now, the next thing we would do here is we have a difference of logarithms. And so that difference of logarithms would mean we have the logarithm of fraction, where actually one of the arguments itself is a fraction. So when we use law number 2, we would have the logarithm of a fraction where the numerator of the fraction is the argument of the first logarithm. And the denominator of the fraction is the argument of the second logarithm. So we have the logarithm of something that's pretty complicated looking. Well, this is the same idea. When we divide by a fraction, that's the same as multiplying by the reciprocal. So this expression that we have written here will have the numerator and instead of dividing by 4 over x, we multiply by the reciprocal, which is x over 4. And then you see immediately we'll have an opportunity to reduce that. Okay, so now we'll have the natural logarithm. Well, what's left over? The square root raised to the 8th power times an x. So let's put that x in front and say then this times the square root of 3x minus 2, and that has a power of 8 on it. And we feel pretty good because that was kind of complicated, but we really can simplify more. So here's what I would like you to consider. The square root of 3x minus 2 raised to the 8th power can be simplified. And to simplify it, we use the idea that square root is a power of 1. So what we really have here is, of 1/2, pardon me. 3x minus 2, instead of saying square root, we'll say to a power 1/2, and that's what we have to the 8th power. Now, in this situation, we multiply the two exponents, don't we? So when we multiply a 1/2 times an 8, we get an 8 over 2, which of course is just 4. So that simplifies to 3x minus 2 to the 4th power, and that's what we want to leave in place of that square root to the 8th power. So we have the natural logarithm of x times 3x minus 2 to the power 4. That's our entire argument. And that's the simplest way we can write that, as one single logarithm. Well, these are taking a little bit of paper, aren't they? So let's go to the next page to do the last one of this type. Okay, I rewrote the directions so that we would remember what we're doing. We're going to write this as a single logarithm, this expression, and of course, I don't have room on the right, so I'm just going to extend down and say what we have is equal to. Now, we have two logarithms, a minus sign in front of, between the logarithms, and so law number 2 would tell us that this is the logarithm, of course it's base 5, of a fraction. But this time, the numerator of the fraction is the first argument that we have here. So the numerator itself is x squared minus 2x minus 3 over x squared minus 4. And the denominator of the fraction is the argument of the second logarithm. So the denominator is also a fraction, which is x squared plus 7x plus 6 over x plus 2. So that's our single logarithm. But of course that argument is a big mess, isn't it? And so we remember, as we've done already a couple of times, when we divide by a fraction, that's the same as multiplying by its reciprocal. So what we really will have here is what we're dividing into, x squared minus 2x minus 3 over x squared minus 4 times the reciprocal of our divisor. And our divisor being below, its reciprocal is an x plus 2 over an x squared plus 7x plus 6. Now, before we do this multiplication, it's going to be a very complicated expression, isn't it? But we understand before we're done here, we need to simplify our argument. And when we are multiplying fractions, what we normally do is we look for the factors of all the numerators and denominators in advance. So we look at this first fraction, x squared minus 2x minus 3 over x squared minus 4, and we recognize the denominator is the difference of two squares. We ought to be able to factor that quickly. Now the x squared minus 2x minus 3, I think will also factor. And I think it will factor as an x minus 3 times an x plus 1. And I think if you check me that you'll find that that's correct. And our second fraction, the x plus 2 won't factor further, so we think of that as one single factor. And the denominator, that trinomial, x squared plus 7x plus 6, I believe will factor as x plus 1 times x plus 6, and you can check that out, I believe. So now we look what's going to happen. The x plus 1 that is in this numerator is going to cancel with the x plus 1 that's in this denominator. Now the x minus 3 won't cancel with anything, but this x plus 2 in the numerator will cancel with this x plus 2 in the denominator. And so we would end up then with an argument that is a fraction where the numerator is simply x minus 3. Denominator is x minus 2 times x plus 6. Now, I'd probably be happy with that solution, that result. We could take one more step. We already know that that fraction won't simplify any further because it doesn't have any common factors in the numerator and denominator. So we could multiply out that denominator, and if we did, we'd get an x squared plus a 4x minus a 12. And that's the single, that's bringing those two logarithms to create one single logarithm, and the argument is in simplified form. Okay, I think that I have one more type of problem that I would like to do, and then I'll close out by giving you some warnings. So let's do that on this on the next page. This is a little different problem, certainly different than anything we've seen. The directions are to express y as a function of x if the natural log of y is equal to the natural log of 17x plus the natural log of c. C just represents some constant, an arbitrary constant. Now, express y as a function of x means that we want to write y is equal to, and over here we have x stuff. Other things maybe, but x stuff. So somehow we need to be able to get rid of, if you will, to get rid of the logarithms somehow or another. Now, let's take what we have, the natural log of y equal the natural log of, let me write it this way, 17x plus natural log of c. And notice that on the right side of this equation, we have the sum of logarithms. And so we could use law number 1 to bring those together. Now, if we do, then that will be the logarithm of the first argument times the second argument. So it'd be 17x times c. Now, I'm going to take the liberty of rewriting 17x times c as 17 times c times x. It's just, that would be a little more clean in what we're doing. Now, there's a couple of more things that we could do here, a couple of choices. But what I prefer to do, to understand completely what's going on, why don't we get these things to the same side? And so what I mean is, let's subtract the natural log of 17cx on both sides, and so we would have an expression that looks like this. Now, the reason I'm doing that is now we have two logarithms again, and then we can bring them together as one. This isn't the only way we can do this, but we can bring it together as one. And so when we have the difference of logarithms, that's the logarithm of a fraction. So the argument of our natural logarithm will have a numerator of y and a denominator of 17cx. And of course that logarithm is equal to 0. Now if we convert to exponential form, that will tell us that our base, and what's our base? Our base is e. It tells us that if we take e and we put the exponent 0 on it, it's going to be equal to this fraction, which is y over 17cx. But e to the 0 is just 1. So what I'm going to do, just because I'm this way, I'm going to put the fraction y over 17cx is equal to e to the 0 on the right side, which is 1. Now, to solve that for y, I would simply multiply both sides by the denominator of that fraction. And of course, that will allow me to have y only on the left side, won't it? So here we get cancellation, so we have y is equal to, and on the right side, we have 17cx. And so we've written y as a function of x. That's what we were asked to do. Now, way back up here, this is kind of like saying 3 to the 2x power is equal to 3 to the 5th power. If the two sides are identical in terms of the base, and we know that they're equal to each other, then the only thing is the exponents of the question, but that kind of implies that the exponents must be equal to each other. Whoops, okay. Well, down here, at this stage, we have the same logarithm, the same base on both sides. One's the logarithm of y, and the other's the logarithm of 17cx, and it says those two logarithms are equal. So we may have been able to go real quickly and say, well, what we're taking the logarithm of on the left side must be identical to what we're taking the logarithm of on the right side. And that would have been much quicker, but I wanted you to see why we can make that statement. So let me end on the next page with some warnings. I just feel obligated to make you realize what we can and can't do. I'm not going to rewrite them, but remember we had 4 properties and 3 laws. In our book may call them all properties, but we had 4 properties and 3 laws. And what I want you to recognize is in none of those did it tell us that we could do things like this. That if we have a logarithm of things added or subtracted, I'm just showing it added here, that would be equal to the logarithm of the first expression plus the logarithm of the second expression. We had nothing at all that told us we could do this. This is wrong. We can't do that. So don't make that jump. Don't try to say that we can. Something else that we never did see, and it's because we can't do it. The logarithm of a fraction being equal to the logarithm of the numerator divided by the logarithm of the denominator. We never saw that anywhere. It's because it's not true. We can't do that. Now, something a little less clear is that we never saw that if we had the logarithm of a number, a variable, an expression, times a number, a variable, or expression that had a power on it, okay? So the power only belongs to the n and not the m. We never said in that case that we could bring the power down, okay? We never said that. The only time we can bring the power down is if the power was on the entire argument, not just a part of the argument. So we never said that. That's because it's not true. We can't do that. And we also never said that if we have the logarithm of a number, a variable, or an expression, and that entire logarithm has a power on it, that we can bring that power down only. Now, this says on the left side, we're taking the logarithm of m, getting a result, and after we do that, we're raising that result to the power p. Okay? In that case, we don't get to bring the power down. The only time that right side is that way is if the power is on the argument. So we're taking the logarithm that has a power of something that has a power on it. So this is not true. So don't make something up that we haven't talked about that we can do. We can't do those things. Don't make up new laws. Well, that ends the discussion, if you will, on the properties and laws of logarithms. So good luck on your homework, and I'm sure you'll do well.